find the truncation error of the Newton interpolation polynomial, we might use Taylor method. So Taylor series, it's help us to drive these errors or truncation error or interpolation or Newton interpolation polynomial. So if you want, for example, to take here first order, second order, quadratic, or for example, third order order. And we know how we can compute the error. So the error, as we said, if we take this our approximation until here, if I take only the linear part, okay, for first order derivative, so the result from here will be the remainder. What I have, so this will be the remainder. If we take, for example, this approximation from here until this point, so the remainder will be the derivative of the function, or the n plus 1 derivative of the function at n plus 1 factorial multiplied by the step size, the difference between the start point and the end point. Okay, and this will be of power n plus 1. Or this step n power, if we have usually in the Taylor series, we have h here, the step size, so this will be n plus 1. So this method, it might be, or we can use it, this one, to find estimation of the error in Newton interpolation polynomial. And we discussed in the previous lecture that the same thing is we can do it for Newton polynomial, because here we have divided difference. So divided difference is not just a derivative. Okay, we have also, this is second order divided difference. This is not just the second derivative. So also we have n divided difference. So it is not just n derivative of the function. So we can replace the divided difference by the derivative of the function, or we can compute the derivative of the function. If, for example, we take the same formula, for example, here, we take the derivative of the function for n plus 1 over n plus 1 factorial. And here we have a parameter zeta, and this parameter zeta should be located between the interval that we have, the starting point and the end point, any end point. So you have here x0, and this will be the n, the point that we want to find. So we need a parameter between them. What's interval that we consider? So this value should be unknown. If we substitute by this value in the solution here of the remainder, should give us the maximum value. But the problem here, because in interpolation polynomial, we have the function in terms of data points only. So sometimes, or in the most of the time, the function is unknown for us. So in this case, if the function unknown, how I will take the derivative for this function? So this is one of the issues that we cannot use Taylor series expansion or approximation to find the remainder of the Newton interpolation polynomial. So the next step, they just replace this derivative by divided difference. So if we replace this derivative now of the function by divided difference here. Okay, so we need here this one. This is the divided difference that again here, because in this divided difference you can see the first term, you have to take f of x minus some parameters. And again, because f of x is unknown or not known for us, because only we have data or data in a table. So in this case, I will have some parameters unknown. Okay, so again, this is unknown. So the easy way is to replace this x, the unknown, with additional point. If you have an additional point from the table, you can use it. We just add an additional point. So I replace this x here, the unknown parameter, with n new data that's known for us. So I know the value of x and the value of x n plus 1. the function at the point x n plus 1. So in this case, this divided difference now, it is known for us. So I can compute this value, and after that the others also, it's known, expect this one, the unknown. So after that it is easy to find it. So this is just approximation that we need. So here it's not what we did. We just replace this one. So that means we have the difference now between the function at n plus 1 minus the function at n. So we just add one term. And this should be precise data that we have. So as a result here, what we have in the truncation error of the Newton's interpolation polynomial. So we replace the function of the data, or the derivative of the function that's unknown for us because the function is unknown, and also the derivative is unknown, by using additional data. And this data, if we use this additional data with divided difference, so in this case no need to know, for example, the function in advance. Okay, so you just use additional data. And this is example how we did this one. So this is the example that we have from the textbook. If you remember this one, 18.2. If we have a table of finding the data, for example, for ln x, and x here is equal to. Okay, so we have the data, for example, at 1 and at 4 and at 6. Okay, like this one, I have the data at 1 and 4 and 6, and this is the function, this one. So by using Newton's interpolation polynomial, so we can find the polynomial here. So if the question after that, this is the data that you have, we know the function now. We estimate the function at n. Function at n, this is the point. So if you went to, this is the approximation that you use, but what's the error? What's the approximation that we have? Okay, because this is our estimation. So the true error, as we said, this will equal the true value minus the approximation that we have. This one that we have. Okay, so this is the true error. So if you want to use the remainder, what's the remainder? So the remainder here, we need an additional point to compute the remainder. The remainder is we need an additional point. So the additional point, we are looking here, we can add it at the end. No need to add it here. Any point, for example, it is 1.5, 3, x at 3, for example, x at 4.5, x at 5, any point, just add it at the end. No need to insert it here. Okay, so for example, if give us the question, give us an additional point at x equal 5. So you can see 5 is less than 6, but we put it here. No need, for example, to put them in order. So if you put it here, so in this case, we just want to fill these blanks. Here I need to find this coefficient, the value of the function. This is given, so it should be given with us. So we want to fill this one. Okay, so that means I will take difference between this one and this one over 5 minus 6. This will give me this coefficient. And then to find this one, I will take difference between these two, this minus this one. Now I will jump one interval, so it will be 4 to 5. Okay, and the last one, this one and this one will take 1 to 5. This 4 to 5 and this 1 to 5. So to find this coefficient, now this is from the formula, I have this is f, or divided difference of n plus 1. This is multiplied by this coefficient now, by this coefficient, x, x0, x1, and xn. And all this x0, x1, and x2 to xn are known for us from the table. Just we substitute. And if I know the value of x, for example, 2, I just substitute by x equal to find the error, like this one. Here, for example, this is the divided difference at n plus 1. And this is the x, the unknown, because the function at 2 is unknown for us. This is x0, x1, and x2. Okay, so we just apply this one. We'll find this the truncation error. So here, the truncation error here is the same in the same order of the magnitude of the true error. If you compute the true error, will be in the same order of magnitude. So this is about the reminder, how we can compute the reminder, and this is very important يا شباب for Bruno. Okay, so this additional point يا شباب. So the data here, desired feature of the interpolation polynomial, the data is no need to have it in order. For example, decreasing or increasing. So any data, for example, it might be in order. It's okay for us, we can apply. Because here the ordering, as we said, is not very important when we discuss these two examples. So if you change the order, it's not very important for us. Okay, so you take this, for example, to finite divided difference and change it like this one. This will not affect the divided difference. Okay, but the point you want to compute should be between the 2 points that you use. Okay, if you want to compute, for example, 2, and this is 1, and here, for example, this is 10, and this is 15, for example, and here you have 9 or anything. If you want to, for example, estimate a value, for example, 9.5, you cannot take it here. Okay, between 10 and 15. Okay, 9.5. This should be intermediate between the 2 points that you select. You might take 9 and 15, or you take 9 and 10. Should be intermediate to have a good accuracy. The other feature here, this desirable feature of this method, additional point set, we can delete with it easy. As we said, we just put it at the end of the table. After that, we just complete the table. No need to insert the point in order. Any additional point, just add it at the end and complete your solution. Okay, so any additional point we can set and treat it easily. So what we have today is Lagrange interpolation polynomial, and this is a sample version of the Newton's interpolation polynomial. So here we just reform or reformulation of the Newton polynomial that avoid the computation of the computing of the divided difference. So instead to have a divided difference, so in this case we try to avoid the divided difference by reform or restructure this polynomial. So it is equal. At the end we should have the same solution. It is the same method. The error should be the same. The estimation should be the same. And but this method it should be easier than the divided difference, because here we don't have any divided difference. We have only the parameters and the functions, and without divided difference, just the reformation of the divided difference. So Lagrange interpolation polynomial, as we said, this is a sample version of Newton polynomial, and this also it is used for curve fitting. So all these polynomials that we study using for curve fitting, that we mean we want to estimate the line. So we have this form of the Lagrange polynomial. You can see here. We have here the function at f of n. That means first order n is determine the order of the polynomial. It is first order, second order, third order, like this one. So we take here summation from I equals 0 to n, dependent on the order, L of I, L sub I, x, f xi. Okay, while L is the weight matrix or the weight coefficient, Li of x, it's equal the product from j equals 0 to n, while j not equal I. Okay, and j here not equal I. So, for example, if you want to find here the first order polynomial, the first order polynomial. So first order polynomial, we just have f of 1. I substitute instead of n by 1. So after that, I will take summation I equals 0 to 1 here. And this will be Li multiply by f xi. Okay, so the first step, what I will do, I substitute instead of I by 0. So I will be L0 fx0. So this is the first coefficient. This is xi0. Okay, substitute instead of I by 0. So we'll have here L0, L sub 0, f of I sub 0. And this summation, so this will be plus the next term, just increment by 1. So here I have L1. So I will be 1 now, f of I1, or f of at x1. Okay, so we finalize with this polynomial. So this polynomial. So after that, this usually f of 0 and f of x0 and f of x1 is given in the table. So if we have table of data like this one, so this is x0. So you have here the function of x0. The value is given. It is y. If you have x1 here, so also the value at x1 is given. Okay, so how after that, how we can compute L0? If you come to L0 here, L0, okay, so here I have I. So this, it's equal. You can see here I have x. So this is from 0 to n. Okay, from 0 to n, we have only n is 0 to 1. Okay, 0 to 1. So here, this is xi. You can see this xi. So this should be x0. I have x here and x0. After that, I will look how many terms we need. If I substitute instead of j by 0, so I should not equal 0. Okay, if I substitute instead of I by 0, j is not equal I. Okay, so here because I have I is 0 and j is not equal I, and j is started from 0 to 1, so just I will avoid 0, I will substitute by 1 only. So I have here only xi. xj is equal x1, and this minus x1. Okay, so here we have xi or li. Li is not equal j. Okay, and j should start from 0, and we avoid j equal I. So here, so the first term, when j equals 0, I will not use. I will take the second term, and this the maximum is 1. So I just have 1. So I have x minus j. I replace j by 1. So here x0 minus x1. Okay, so this is for L0. So just we use this for. So this will be the value of L0 that we've given here. The same things, if you want to find, L1. Okay, so L1, again, I have here this coefficient is x, and this should be x1 directly, this x1. After that, this xj should not equal x1. Okay, xj should not equal x1. So here what we have, I have j is from 0 to 1. So I have j equal 0 and j equal 1. So in this case, I will take j equal 0 only. And here, this equal 0. Okay, so this is L1. So I have L1, 2 terms only from 0 to 1, because I already equal 1. So I have here x and 1. So in this case, j will equal 0 only, because j should not or not equal 1. So at the end, I will finalize with this form. From the table, it's easy. Without any divided difference, I just substitute. I have the value of x0. I put it here. The value of x1 here and here. And the function is given. This is the x is unknown to build the polynomial. After that, if I want to estimate the value at this point, I just substitute by the value of this point, and then we find it. Okay, so this is the general form of this one. If we have a data points like this one, so to find the polynomial using Lagrange interpolation, so this is the form as we said. We have here the function, and this is the weight function, and this is the function at x size. This is given, and here we just want to rewrite a weight matrix or a weight function. Okay, this is the very important thing, so we write it correctly. So this is another example. If you have this example, let's put it in table, will be easy. So this is x, and this is f of x. So we have 2 points now. I have x equal 2 and f of x equal 4. And this point I have x2 equal 5 and y equal 1. Okay, so this is the data that I have. So here the question is to derive the linear Lagrange interpolation polynomial. So from the linear, as we said, we need this polynomial. If we remember this one, I will address this. Okay, I'll paste it here. So this is the linear Lagrange interpolation polynomial. If you look for this one, this is the equation, because here they ask for linear. So we have n from 0 to n is equal 1. So we take the product from 0 to 1. So we take 2 terms. Okay, the number of the terms is n plus 1. So here I have n L0, and L0 it's equal x minus x0, x1 over x0 minus x1. So here I have x, this is the value of x, it's unknown, minus x1 is 5 in the table, over x0 is nothing, just 2, minus here x1 is 5. Okay, so we just put this as a equation or unknown. If I know the value of x, it is easy to substitute by the value of x. Okay. If I don't know the value of x, we put it in general form. After that, we compute L1. Okay, to compute the L1 is nothing, just x minus x0. x0 is 2 over x1 minus x0. As we said, xj should not equal xi. So in this case, to avoid 0 at a denominator. So as a result, if I compute the value of L0 and L1, and f of 0 is given here in the table, and f at x1 is given here in the table, this equal 1 and this equal 4. So here I have 4 and this is 1. The functions, I just multiply and reorder or redo rearrangement of the equation. So at the end, this will be the linear equation by using Lagrange polynomial. Okay, so this is the polynomial or the equation or the fit equation or the curve fit by using this data. If I have this data, I can get this equation. And this the graph just represent the Lagrange interpolation polynomial or the curve fit of these points by using Lagrange method to give us this line or straight line equation. Any question until here? Any question until here? Okay, let's take another example. This is another example if given this data. So this is a table that you have. Okay, so this is the x's and this is the y. Okay, so again, ya shabab, if you want to find the polynomial here, we just apply this equation. You should know how you derive this equation, and usually it's given in the general form, or sometimes we give you this, for example, specific equation. So here what we want, I want firstly to compute L0. Okay, so L0 nothing, just equal x minus x1. x1 is 2 or 5. Okay, and this is over x0 is 2 minus 5. Okay, so after that also Lx1 we do it the same. So we have here x minus x0 is 2 over Lx1 should be 5 minus 2. After that we just substitute from the table that we have. Okay, شباب. So if you do this one by this substituting by compute here, this is v1 versus v0 is just L0, and this is v1 is L1. Some they use v's or some they use l's. Okay, so any form we can use. Okay, so at the end just we substitute and find this one, and we know the function at x0 and x1, and after that we just substitute to find the interpolation polynomial. Okay, so this is for the first order. We can solve the previous examples that we have for Newton's interpolation or for divided difference by using this method. We should have the same solution, or we should get the same solution. So if you want, as usual, if you want to improve the accuracy, so usually we go with highest order. Okay, highest order. For example, here we can go with the second order polynomial. Second order polynomial, we have f2. Or stated this, we use f2 to represent we have second order polynomial. So that means I will take summation from 0 to 2. Okay, that means I will get three terms. I have L0 f of 0 plus L1 f of 1 or x1 plus L2 f of x2. Okay, so after that we went to L0. If I look for L0 here, I take here the product from 0 to 2. Okay, so this will be, here I have x and this is xi. So I is equal 0 already, so this will be x0. So what's the numbers that I have? I have 0, 1, and 2. So here we have condition j is not equal 0. So what's the option here? I have x equal 1. And I protected this, I have x minus x2 and x equal 2. Okay, so the option that we have only because I equals 0, so this x and x0, so this minus xg, x sub j. So sub j here because I have only 3 points from 0 to 2, and I already equal 0, so j is not equal 0, should not equal 0, so I have only 1 and 2, so I just substitute, and instead of j equal 1, and then j equal 2, so I will get 2 terms, multiplication of 2 terms. So this is the value of L0. The same things we do it for L1. Okay, for L1 the same. So j or I already equal 1, so I will have x over x1. So this is minus kj over L1 or x1 minus kj. Okay, so here I can substitute instead of j by 0 and substitute instead of j by 2 only. So I have two terms. So we do the same for L3 like this. So this is the form for quadratic polynomial. Okay, so if you want to substitute here, let's pick this one. Use it in the next slide in this example. Okay, so here, for example, if you want to find a second order polynomial using Lagrange by using this data, I have x's and I have y's. So as we said, I have here L0. L0 is equal x minus x0. Okay, and x0 is equal 1 over 4 over x minus x1 is 1 over 4, x0 is 1 over 3, and x1 is 1 over 4. Like this one, I substitute here, and here again I have x minus x2 is 1 over x here should be x0 minus 1 over 3 minus x2 is 1. The same things we do it for L2 and L1. After that, we just substitute, and f of x0 is given here is equal to, and f of x1 is equal minus 1, and f of x2 is given here is equal 7. We just substitute in this polynomial. So this polynomial, just the polynomial that's connect all these points or fit all this data. Okay, because this is interpolation, so it is connect all these points. So it give us this polynomial. After that, if we know the value of, if I want to estimate the value of x or the value of xn plus 1, if I know the value of xn plus 1, so I just substitute by the value of x to find the estimation of this value of this function. If we return back to the example that we did before by using divided difference, we can solve it again by using Lagrange interpolation polynomial. So if you want here to find or using the first and the second order to evaluate the ln2 from the textbook that we have. So it is given here we have 3 data points. We have x0 at 1, x1 at 4, and x2 at 6. Okay, so the question is asked to find the first and the second order polynomial. So the first order by using Lagrange is given by this form. Okay, this L0, L1, f of x0, and f of x1. So here, the question is to estimate the value at x equal to. So x now is given. So I substitute instead of x by 2 minus x1. x1 is 4 over x0 is 1 minus x1 is 4 multiplied by f of x0 is 0. So this will be 0 plus x is 2 minus x1 is 1 over x2 is 4 minus x0 is 1 multiplied by the function at x1 which is equal this number. So after that we get this estimation. So next step to compute the second order. This should be second order here. Okay, this is the second order. Okay, second order. Second order polynomial here. So in the second order polynomial, we use this form of Lagrange polynomial. So again here, I have the value of x, so is equal to minus x1 is equal 4, multiplied by 2 minus x2 is 6, over x0 is 1, x1 of 4 multiplied by x0 is 1 minus x2 is 6 multiplied by the function at x0, which is 0 here. So this will simplify everything. So this will goes to 0. After that, we'll go for the next term to compute L1. L1 is nothing, just x minus x0. X is 2 minus x0 is 1. Multiplied by 2 minus x2 is 6 over x1 is 4 minus x1 x0 is 1 multiplied by x1 is 4 minus x2 is 6. Multiply this by the function at x1 is this parameter. And this will be the additional term here. here we have x is 2 minus x0 multiplied by x minus x1 over x2 minus x0, x2 minus x1 multiplied by the function at x2. So this will be the estimation by using the second order. Okay, so we have the estimation when we use the first order and also when we use the second order. Okay, so after that, if you want, for example, to check the error at, for example, the 2 points. So here, this is the estimation of this value by using the second order, and also we have the estimation of this value by using the first order. If we know the true value by using the calculator, for example, we can compare the percentage relative true error or the true error like this one. Any question until here, يا شباب? Any question? So this result, we should expect this one to be the same results that we get it by divided difference method. Okay, we should have the same results by using the divided difference method. Okay, so if we look for this graph, this represents the polynomial that we have. So when we use only first term, you can see this is the estimation of the first term is because this one. Okay, it's connected only one data point. Okay, or cross one data point. And here, this when you use second term, you can see it is cross a single data point. When you use the third term, we cross here a single data point. So this is the polynomial. This is the assumption of the three terms. Summation of the three terms. If you sum the three terms in the second order, so this will connect the 3 points. You can see connect this point and this point and this point. Okay, so if you use one term only, so you connect only 1 point. Two terms, you will connect 1 point. So each term connect, it's draw a graphs that's connect one of the data. So this term actually draw a graph that's connect one of the data. So this term will draw a graph that's connect the second data. This term will connect a graph that's connect the third point. So if we sum them, I will get one polynomial that will connect all the data. Okay, so this is the idea of this interpolation polynomial. So this, the summation of the 3 points must therefore be a unique second order polynomial that's passed exactly through the 3 points. Okay, should pass through the 3 points that we have. Any question? This is one of the codes that's usually used. Sometimes we have some tools already available in this language or MATLABs. We have some already codes there. For example, we can use some commands that it help us to run that logarithm directly because the function is already developed or implemented there. And some function we need sometimes to implement it again. For example, here, this is one of the codes developed for Lagrange polynomial, interpolation polynomial. So what we need here, we need the x's and the y's, the data that we need. Okay, and the size of this one should be the same. After that, this is the number of iteration, and this usually the order that we want to of the polynomial that we have. So if we take the iteration, we can say for I from 1 to n, this is the weight matrix. We start with initial values 1, Li. After that, for L 1 to n, or j from 1 to n, if j is not equal I, so compute the weight matrix. So this is the weight matrix, we have it. This is x in initial minus xj over, or this is the point that we want to estimate, x initial, that we want to find, minus xj over xj minus xi minus xj. Okay, so we end the f, and after that we end the 4 and we end the first 4. After that, Ly is just equal a sum Ly that we have multiplied by the x's. Okay, so Ly is given here, already is given. So you just pick it from the column, we take it point by point, because here the product is point by point. It's not multiplied by product. That means we take point by point. So I will take xi or y1, y2, y3 like this one, multiplied by little matrix. So this will give us this polynomial of using Lagrange polynomial. Any question? Any question? Okay, so this is another example for finding the polynomial interpolation by using both Newton's divided difference and Lagrange interpolation polynomial. The methods, these methods must give the same answer. Okay, both must give the same answer if you use the same data and the same order of the polynomial. So here, for example, if we have this is the x's and this is the y's that we have, by using the divided difference, as you know, we need the regression table. Usually I will give you the regression table in the exam or the quiz. So this is, for example, the regression table. After that, we fill this coefficient, the first order divided difference. I use these samples. Second order divided difference, third order divided difference, and this is fourth order divided difference. Okay, so as we know, this coefficient 2, for example, is 3 minus 1 over 1 minus 0. This minus 1 is 2 minus 3 over 2 minus 1. 3 is equal 5 minus 2 over 3 minus 1, like this one. So this is minus 1, 4 minus 5 over 4 minus 3. So after that, we compute this coefficient, just equal minus 1 minus 2 over 2 minus 0. 2 is equal 3 minus 1 over 1, 3 minus 1. Here I have minus 2, I have minus 1 minus 3 over 4 minus 2. Okay, so the same thing is we do it for this coefficient. So we take the difference between these two, 2 minus 3 over 2. So now we need to take, we jump to, okay, so this we take 0 to 3. And this is minus 4 over 3 is equal minus 2 minus 2. I will take 1 to 4. Okay, so the last term we should take the entire run. So in this case, to compute this one, I will take difference this one minus this one over this coefficient 4 minus this coefficient, the maximum run. Okay, so this will give us the table. So after that, to write the polynomial, as we know, what we need here, shabab, here from the table to write the polynomial. Where is B0? What's B0? B0, B0, yes, 1. And B2? B1, sorry.
B1 is 2, and B3 is minus 3 over 2. That's
okay. It. Yeah, okay, thank you. Thank you. So this is the first row here, shabab. We need the first row. This is B0, B1, B2, okay, B3, like this one. Okay, so we need this, the first row or the coefficient that's contained x of 0. So this one, I just put it in the Newton's interpolation polynomial to find the polynomial that we. Okay, so this is the table. Again, we need to do this one by using this one. This is the b's, and this is the polynomial that we have. So this is the first order polynomial by using these data. Okay, so as we said, the first row, it gives us or help us, for example, to identify the piece. If we identify the piece, so after that we can use just we type it in the polynomial form. I have here f of x0, and after that b1 multiplied by the difference, because here x0 is equal 0, so this minus 0. Okay, because here I have x0 equals 0. Okay, so you can see x0 is equal 0. So here you have 2 multiplied by x minus x0. So x0 equals 0. So we just type here x. Here also x, because I have x minus x0 multiplied by x minus x1. Okay, so this also x minus x0 multiplied by x minus x1 multiplied by x minus x2. And x1 is equal 1, x2 is equal 2. Take this. After that, we finalize this one, and this will be the polynomial. This should equal the polynomial if we use Lagrange. Okay, so if we have first order or fourth order here, so this will take from 0 to 4. Okay, so we have 4 terms. We have L0, L1, L2, L3, L4. Okay, so this one, L0 should multiply by f at x0. x0 is 1. L1 multiplied by the function at x1, it's equal 3 from the table. This is equal 3. I should pick the table here. Okay, so this is 2, not just the function at x equal 2. L5 is not just the function at x equal 3, and 4 is not just the function at x 4. Okay, so what we need here, just we need to compute this coefficient L1, L0, L2, L3, L4 by using this the weight matrix or the weight parameters or factors. So the L0 we can compute it here. We can compute it here because here I have this is x0, so I will take x minus x1, x minus x2, x minus x3, x minus x4. Okay, over x0 minus x1, x0 minus x2, x0 minus x3, x0 minus x4. Okay, these zeros are x0. So after that I will get this term. L2 or L1, I have x minus x0, L minus x2, L minus x3, L minus x4. Here I have x1 minus x0, L1 minus x2, x1 minus x0, x1 minus x2, x1 minus x3, x1 minus x4. So the same things we do it for these terms. After that, we will have these coefficients for L by putting here, by substitute instead of these L's or weight terms inside this polynomial, and by do rearrangement, we should get the same answer, or we must get the same answer at the end. Okay, okay, Shabab, so both results should provide the same answer, or must provide the same results at the end. Any questions, Shabab, until here? So what about the error? The error, what about the error? So the error we do it in the similar way. Okay, like Newton's polynomial. Here we take the product, and this we find the function here, like the divided difference. Okay, so or we can use it, for example, like Taylor method. In Taylor method, we have the function, for example, but here the function is unknown. The function usually is unknown. So if we have the function here of order, for example, n, but if you know the function, it's easy, but the function usually will be unknown. Okay, so this, if the absolute value of the function after we substitute and instead of x, or usually we said this zeta, and we find the maximum value of this point, and after that we substitute in this form, so we should find the value of the error. Okay, and we assume here this is the absolute value of the n plus 1 derivative of the function at x should be equal or less than m. So what's m? M is just the maximum value that we have. Okay, so here if we go to this one, if you go to this example, So for example, here the function is given sine x, and we want to use the 9th order derivative. Okay, so here, if the function is given, so it is easy. I know the function, so it is easy to find it. But if the function is not given, so I don't know. Okay, so if we take the derivative of the function first to the 9th order, okay, so you will get the 9th order is equal sine of x. Okay, so the first derivative here is equal cosine. After that, sine x. After that would be minus sine, second order. So to the nth order or the 9th order, so this will be cosine sine x. Okay, 9th order will be sine x. So the question here is to find the error at this interval. So the first step, what we want to find the maximum value here, or the absolute value. When you substitute instead of then sine by 0, and maximum value when you substitute instead of x by 0.1957. Okay. So the maximum value, if you substitute instead of x by 0, so we will get 0. If we substitute here in the interval, and if we substitute instead of the 1.6875, I will get almost 1. So it's like 9.8 or something like this one. Okay, so I will get a value near to 1. So this value, m, I equalize m, make it to the nearest integer. So m now becomes 1. Okay, m becomes 1. So now I just substitute in this form of the error. We have n is equal 9, and I have m is equal 1. So I put here 1, and we have 4 multiplied by 10. And this is the interval b minus, or the width of the points I have here. This is the width, this is the line, this point and this point. So to compute the width between the 2 points, 0 and this point 6875, so this is equal to this one, 1.685. So over n, and we'll take this to power 10, so this will be the error. Okay, so this will give us the error if the function is given. If the function is not given, so we need to find the divided difference like this one in this form, or we use additional data like what we have before. Any question about this example?
Yes, lecture here m it's represent what?
M is represent the maximum value here. The absolute value when you substitute instead of x by any value inside this interval. You have the interval from 0. You look for here from 0 to 1.6875. So we need the maximum value. If you substitute, for example, of 0, what will be the value? We need the maximum value of the table. You need to substitute here, for example, x equals 0, equal 0.5, okay, equal 0.8, equal 1, and the last term should be equal 6.875, okay. So we substitute instead of x by values in this interval from 0 to 1.687. So we need the maximum value. So the maximum value, it's represent m. The absolute value, it is negative or positive. We need the absolute, the maximum magnitude. The maximum magnitude. So here, for example, in our example, when we substitute instead of sine, because the 9th derivative of the sine wave, it's equal sine wave. So if we substitute instead of x in sine wave, this will give me 0. But when I substitute instead of b here, it gives me the maximum value. It is 0.998, for example. Okay. So in this case, I will take m. So m should be greater than or equal. M should be greater than or equal this one. If this is equal 0.9, So we select the m is greater than, or usually take the nearest integer. Okay, so here we have m equal 1 in this example. We take m equal 1. So it is equal or greater than, so we take it with the nearest integer. So we consider it as 1. Okay, so after that, just substitute in the form that we have here. So we just substitute, and instead of, after I find the nth derivative, the derivative order n, we do derivative 1, second, third, 5, like this one. We'll get this polynomial. After that, you substitute. The theory in the book is that it should not be, it should be between these 2 points. Okay, should be between these 2 points. Sometimes, to save our time, we substitute by the upper bound and the lower bound, and we see which will be the maximum value. And after that, we find the maximum value and we substitute here. Okay, so the m, as we said, is just because I substitute, and instead of this derivative by 1.6875, I get 994. It should be 994, I think. Okay, so I get this one, and as we said, m should be greater than or equal this number, so we just round this. We round this to 1. And after that, you just substitute, you find the value of the error. That's it. But here is the function is given. If the function is not given, this is different criteria. So we need to use divided difference. Okay, Shabab? If the function is not given, you have table, you have to use divided difference, or you should use divided difference. If the function is given, you can take it using Taylor method and you solve. Okay, so
Doctor,
yes, hold
for m, we will substitute sine x to the power 10
which one?
for m.
No. We take the nth derivative, derivative order n, not the sine of power 10. This n order derivative.
Yeah.
Okay, you take the first derivative cosine, second derivative minus sine, third derivative minus cosine, fourth derivative sine, fifth derivative cosine, like this one, until you get the derivative number n, you will get sine. You should get sine. Okay, we take derivative.
Okay, and 1.6875 by radian.
Which one? Yeah, radians. Yeah.
Okay.
I just check it. Yes, I used the online calculator. It is radian. Yeah, should be. Should be radian. Yeah, تفضل. You have a question?
Why are we using this formula?
This to compute error if we have if we know the value of the function of the interpolation polynomial. Okay, that's we use this one to compute the error if we know the function. So if you return back, you can see here if the function is known. So the error in interpolation theorem, this is using interpolation theorem. If the function is known, this is different from what we study in this chapter. We study in this chapter the function is unknown because we have data only, discrete data. We want to estimate the function. But the question here, assume this type of question, they assume if the function is known. If you get the function or the exact function by using interpolation polynomial, so this is the way to compute the error. If the function is unknown, you use only the divided difference. What we did in interpolation, Lagrange, if the function is unknown, because we don't know the function, we have only data points. So I cannot take any derivative here because I don't have the function. So we use the divided difference. and we take the product here to compute the error. But here, this theorem also suggests that or propose that if the function is known for us, we get it by using interpolation polynomial. So I can compute the error by using this form. So that means the error, this is the function, the actual function that I have, the true value, or this we call this the truncation error, minus this is the approximation, the polynomial that we compute, this is our approximation, the polynomial that we compute should equal this coefficient, this term. So here the main point, I want to compute the value of m or estimate the value of m. The value of m is the maximum value. When I take n plus 1 derivative, after that I will substitute an instead of x by values in this interval. What's the interval that I have? Here I have the interval from 0 to 1.6875. I will take points by points, I will substitute in this interval. What will be the maximum value? So this will equal m. So m is equal or greater than this value. So for example, for sample version, I will take the lower bound and the upper bound. If I substitute instead of x and the nth derivative by 0, so this will go to 0. If I substitute here instead of x here and the nth derivative by 1.6875, I get 0.994, almost 99.4. Okay, and the theorem said it is m should be greater than or equal this coefficient, not less, equal or greater than. So in this case, I just round this off to 1. I have 99.994, so I round this to 1, so I have m equal 1. This is the idea. After that, we just substitute in this form. So this is the error, this is the true, and this is the approximation. And what we want here to compute the truncation error. Okay, the truncation error should be less than or equal this number. Okay, L is given. N is nothing, just the order of the derivative. LB is B minus A, just the width of the data. I have N plus 1, all known. Just I want to find the M here. So this is a suggestion if we know the value of the function, if the function is known. But what we have in this chapter, usually all the data is unknown, the function is unknown. So if the function is unknown, we have only discrete data. So in this case, we use the divided difference, okay, or finite divided difference here. Clear this point, Yeshua? I hope it is clear, inshallah. So what's the last topic here in this chapter? If we need to find the inverse interpolation. So that means if I know the value of the function at xn, I need to know the value of xn. What's the value of xn? It's like we compute the roots of the polynomial. You know the function and you want to find the value of x. Okay, so the question, what is the limitation of the inverse polynomial? What's the original function has inverse of x most and y1 and y2 should be must be distinct. Okay, so this is usually a solution or one of the traditional questions that we have. If we have this data, this table of data, okay, and we find using this table and we compute this polynomial. This is the sample approach. If we, for example, fit the data using a quadratic polynomial by using 3 points only, if I take these 3 points, 2, x equal 2, and x equal 3, and x equal 4, these 3 points, if I consider these 3 points, I get this quadratic polynomial from 3 points. So this is the solution. So now the question, if the function is equal 0.3. If the function is equal 0.3, so what's the value of x? Okay, so now I have the function equal 0.5, I have the function equal 0.333, I have the point y or equal 0.25. So I want to use it inverse method if the function equal 0.3. So what's the value of x? So this is the inverse interpolation. So what we do here, I just substitute instead of f of x by 0.3. After that, we just compute the roots of this polynomial by using the quadratic form. Okay, so sample way by using the quadratic form that we have. Okay, so we find the roots here of this polynomial. So because this quadratic second order, I will get two roots. This is the first root and this is the second root. So, so the second root is a good approximation of the true value, and the true value should be 3.33. Okay, 3.33. This is the true value. This x should be equal this one. This is the true value of x. If x is equal 3.33, the function will equal 0.3. So our approximation is give us this value. And 5.7 is so far from this point, so we just select the good approximation at this one. This is one way, but we do it like this one. Okay, we do it like this one. So by get the polynomial, apply the polynomial, for example, second order polynomial. After that, replace y or f of x by the value of the unknown. For x, for example, the function at this unknown. After that, we find the roots of this polynomial. We get the roots. One of the roots should be the solution. One of the roots should be the solution. Another method is very simple. What we do here, we just inverse the interpolation. So if you have this is the columns for x and this is the columns of y. So what we do, we just interchange or exchange the roles of x and y. So I will make y's as x and the x's as y. Okay, so I just do interchange, and this is the sample way. This is the x's and this is the y that I have. I just interchange the roles, so that means I will make the x or the y's becomes now x and x becomes y's. After that, I will evaluate the function and to find unknown, and this I think sample method. So the inverse Newton interpolation polynomial, it's given like this one. So before we have here f of x0. So now I have x0. Before we have x minus x0. So here we have f minus f0. So like this one. And we take a divided difference in terms of the functions, not in terms of the x's. Okay. And here the divided difference, you can see it is x divided difference. We take it in this form. Let's see this example. We have another example. Also this for Lagrange, we do it the same. Okay, just we change it and we put it in this form. So let's look for this example, ya shabab. This is I have this is the x's that I have, and this is the y's that you have. Okay, given the table, find the value of xg such that we give us the value of xg, the function at xg it's equal to 0.5. So now this is the inverse, because they give us the function and they ask us to find the independent. So in the solution, ya shabab, just reverse here the table. Usually we type here the x's and this is the y, just interchange between them. So type here this is the y's and this is the x, and work on this. So this is the y bar and this is the x bar, and you continue from this one. So this is now your x's and this is your y's. Okay, so after that we do a divided difference, a regression here. So this coefficient I can use it. I have 2 minus 1 over 2 minus 3.2. So this should give me this number. I have here 3 minus 2 over 1.6 minus 2. So it will give me this number. After that, I will say minus 2.5 minus 0.8333 over 1.6 minus 3.2, so this will give me this polynomial. Now يا شباب we have this polynomial because here I have a b0 is equal 1, this b0, and this b1, and this b2. So b0, b1, and b2, just substitute this b0 and this is b1 multiplied by, now instead of x we have y, so y minus x0, I have here b2, y minus x0, y minus x1. Okay, so like this one, I'll just substitute now instead of y's here by 2.5. So we get the value of x is equal 1.2187. Okay, so this is the value of x. So by using the inverse polynomial, user in the exams, we give you data like this one. Just interchange between them. It's not that difficult. Interchange between them, and after that you apply the divided difference or Lagrange method. You apply it, and after that you find it. If you have second order system, because this is easy to find this one, the roots, I don't know how many order you can find, for example, second order, third order, I don't know what's the calculator or the type of the calculator that you don't have these days. And for the development of the technology, they have some calculators, they compute third or more, I don't know. I know they can compute the second order of the roots for the second order. So here, for example, we can find it, the roots of the second order. The nearest one will be, here we need to know the true value. After that, we select one of them. Okay, but this method will give us a good estimation. Will give us only a unique solution, one solution, no two solutions. The quadratic will give you two solutions, but this will give you only one solution here. So in this case, this will be your approximation. Okay, and this should be comes with the minimum error. Any question, Shabab? So by this slide, we finish unit number 6.
Doctor.
Yes.
Now, which procedure should I take? This method or the first one?